Thermodynamics. Now, one of the most important concepts in physical science, whether it's physics, chemistry, you name it, right, is this idea of thermodynamics, because at the end of the day, thermodynamics answers a very important question. Why does stuff happen? In other words, have you ever sat there and thought about, like, for example, if you take a ball at the top of a hill and you push the ball down, right? Just give it a little bit of energy, a little oomph. What you expect to happen is that the ball is going to, by itself, roll all the way down to the bottom of the hill. It's going to come up a certain amount, but then you could probably predict that it will slide back down. And it might do this back and forth and back and forth and back and forth until eventually you can almost predict that the ball will kind of end up at the bottom, at the valley of, let's say, that hill. And so the question is, well, why is that an of course, right? Of course it happens that way. And you might be thinking, well, gravity's pulling the ball down. It's going from a place of high position to a place of lower position. Sure, yes. But really, when we get down to it, the question that we're asking is, what is the spontaneous process that will happen? What is going to happen without us having to do anything else to it? So another example of that might be something like, if you had a balloon totally filled up. So if I blow up my balloon and then I pinch the end of it, right? Well, what happens the minute I let go of the balloon, right? You know that spontaneously the balloon's going to go flying off, right? You know that that's going to happen. But you understand that to be true because you've been in this universe now for quite a bit of time. And you have been observing and seeing spontaneous processes occur all of the time. So when we talk about thermodynamics, the reason why this is a mission critical and very important topic is because thermodynamics starts to give us some of the tools to understand why certain things occur and why other things do not. So, as an example, I can expect that on a very cold day, right, if the temperature is below freezing, so if it's under 0 degrees Celsius, if I leave a cup of water outside, I expect that after a little amount of time, a couple of hours, that glass of water is going to be frozen, right? All of the water will have spontaneously turned into ice. I could also expect that if I take that glass of water from outside and I bring it in to my house, right, and I leave it on the kitchen counter again for a couple of hours, I expect that spontaneously that ice will melt, like it will automatically become liquid water once again. Right? It would be very weird if I took water from, let's say, outside, brought it and put it onto my kitchen counter, and then it froze. You would be like, that makes no sense. Likewise, it would make no sense whatsoever if I took an ice cube from my refrigerator, brought it outside where it's below freezing, and now it's melting. Again, that makes no sense, right? So this idea of spontaneity, right, is at the core of what we will be discussing and describing in this unit of thermodynamics. That's the big picture, right? But we're going to be talking a lot about, at the end of the day, does a process occur or does a process not occur? Is something spontaneous or is something non-spontaneous? Now, in order to understand whether a process is spontaneous or not, whether it occurs or not, we're going to have to break down some of the fundamental laws of thermodynamics. And in this unit, we're going to be talking about the 3 fundamental laws of thermodynamics. The first one we've actually already discussed, because the first law of thermodynamics we learned way back when we were discussing thermochemistry. right? Or this idea of that in every chemical process, in every chemical reaction, energy is going to either be absorbed by the chemical reaction or it'll be released by the chemical reaction. So if you recall, this was when we talked about, is the reaction endothermic? Is the reaction exothermic? So all the material that we talked about in thermochemistry way back when, all of this is actually the first law of thermodynamics. The first law of thermodynamics states exactly what you see here. Energy is neither created nor destroyed in a chemical process. It's basically the law of conservation of energy. So if you recall, this is how we did calorimetry. So for example, we could sit there and say, hey, the amount of heat that a system released had to equal the amount of heat that the surroundings absorbed. This was a fundamental principle in being able to measure heat transference, right? So the only way we could use a calorimeter, the only way that we could sit there and figure out how much energy was moved before and after, right? How do we kind of go one way or the other, was because we used this idea of the first law of thermodynamics. Energy is neither created nor destroyed. Recall that since energy is neither created nor destroyed, this eventually led to our understanding of changes in enthalpy, delta H. So again, enthalpy is going to play a massive role in answering the question of, is a process spontaneous or not? So what's critical to be aware of here is that we can't just throw away everything we saw from before. We still are very much dealing with enthalpy changes and joules, right? So how much energy is coming in, how much energy is going out. That's going to play a critical role in thermodynamics. And so now we get to the weird part, because this is going to be completely different from anything that we've ever mentioned this entire year of chemistry. So, the second law of thermodynamics states the following: the entropy of the universe is always increasing. What the heck is this word over here, entropy? What do we mean by entropy? What on earth does it mean that the universe, how do we even define the universe, that the entropy of the universe is always increasing? So to help us, first and foremost, let's focus on what we have down here. Entropy is the amount of randomness or chaos in an object, reaction, system, you name it. Now, we're going to spend the next episode really breaking down what entropy is. But for now, let's just keep it as simple as possible, right? And let's just try to build the picture or idea of what we mean. Every single system, every single object, every single reaction has a certain amount of, and I'm going to use a very broad word here, structure. It has a certain amount of organization. So for example, you might be looking at me right now on your desktop or your laptop or your phone. Well, that object that you're looking at me with right now has a high degree of structure. Just stop and think about it. There's circuitry in there and a bunch of microchips that are doing their jobs, right? There's a screen that emits a certain very regulated amount of light particles that allows you to see these images. There's a speaker that is vibrating with a certain frequency so you can hear me and understand me. And all of that is not just sheer coincidence. A lot of work had to go into creating that structure. Make sense? Or a lot of work had to go into creating that amount of order. So when we talk about entropy, entropy from a physical science perspective is all about randomness, right? The more random or disorganized a substance, a reaction, or a system is, then the greater its entropy. The more structured or organized a substance, reaction, or system is, then the lower the entropy of that object. So what we'll see in our next episode is that when we talk about the second law of thermodynamics, what we have to do is we have to compare the entropy of a system versus the entropy of the surroundings, and then we get the total of those two gives us the entropy of our universe. Now here's the deal. The second law doesn't say that a system always has to become more chaotic or random. It doesn't say that the surroundings have to get more chaotic or random. But what it does say is that the entropy of our universe, right, the total amount of it, the entropy of the universe always must be expanding. So our universe is always becoming more chaotic and more disorganized. And so what we'll do is that we're going to take a moment now in the next episode and we're going to break down what do we mean by the system, the surroundings, the universe, and why actually the second law of thermodynamics makes a lot of sense to you. You've actually known about the second law of thermodynamics your entire life. You just never had the words really to describe it in a way that we could measure it. So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.